Decline curve analysis is useful for estimating a well's ultimate recovery, EUR, and generally follows a hyperbolic, harmonic, or exponential trend. Arps equations are used to fit the decline data and requires four variables, which are initially approximated and later refined using the solver plugin. In 1945, Arps published his paper where he shows how to solve for hyperbolic, exponential, and harmonic shapes, as we can see in the lower left figure. The formula used for these curves is where Q is the modeled production rate in stock tank barrels per day or standard cubic feet per day, T is the time in days, Q sub I is the initial production rate, D sub I is the initial decline rate, and B is the decline exponent. The decline function is known as the hyperbolic decline function. The initial production rate, Qi, fixes the intercept. The decline exponent B shifts the late stage production rate up or down, where B equals 0 is exponential, B equal 1 is harmonic, and B between 0 and 1 is hyperbolic. In the exponential case, where B equals 0, a zero divide error will result in Excel. So a very small number can be used instead, or a modified equation as given in the Excel worksheet that we'll look at shortly. The initial decline rate, DI, is generally a small number, less than 1%, or 0.01. Fitting a line curve requires solving for three input parameters, Qi, Di, and B. The interpreter makes an initial guess at the parameters and calculates the percentage error, which is the difference between the measured and the modeled values. Subsequently, Excel's solver plugin can solve these inputs by minimizing the sum of the errors to 0. Once Arps production rate Q is solved, the cumulative production forecast can be determined using the following equation, where QP is the cumulative production and represents the integrated area under the rate decline curve. Qi, Di, and B are the solve parameters from the above, and Qf is the modeled forecast production rate, or Q, solved above. So let's look at the example in Excel. Excel worksheet, I'll demonstrate how to solve for a decline curve analysis for the observed gas rate production from a well, which we see here, and where the raw data is shown in the table to the right. We'll use the Arps decline curve analysis function shown here, and the cumulative production rate formula shown here in this analysis. Before we do this analysis, let's look at this chart here where I've used a Python script to solve for the decline rate using three different exponents, 0.5, 1, and a very small number to represent the exponential. Alternatively, you can use the exponential formula shown here. And as we can see, B has the effect of moving the late stage production up or down. So the first thing we need to do is we need to make some educated guesses. What's the initial production rate, Qi? In which case I'm just using the first observed or the highest rate observed. The next thing we need to know is what's the initial decline rate, the Di. And I'll show you some examples for estimating this. So let's scroll down a bit. And here's an example of the solution. We'll come back to this. But what is this initial decline rate, Di? When production is plotted as flow rate versus time, the initial decline rate, Di, is equal to the slope of the tangent point along this line, i.e., the time divided by the rate at that point. Or we could say that Di is equal to the y-intercept divided by the x-intercept divided by rate at some point on that line, which we see in this chart. Some interpreters look at the initial decline rate at 30 days of production, some at 60 or 90 days. It's your guess as to which is the most representative value. And what I've done here is, to make some guesses, I've picked some points along where I think that curve should be, and I've drawn a straight line along the tangent for this point X, Y, and Z, and then at 30 days up here. Once I've drawn the lines, I just pick the y-intercept and the x-intercept. And in the table below here, I've calculated the initial decline using the x-intercept, y-intercept, and rate at the point. And you can see that I get quite a difference in the estimated b values. An alternate method is to fit the exponential trend line on a semi-log plot and use an exponential value. In this case, it would be 0.002, as I show in the example here. The estimated DI is the absolute value of the slope. So here, though it shows it as minus 0.002, you would use 0.002. DI can be estimated using Excel's Linus function as well, and taking its absolute value. This eliminates the need to chart the data to solve for the slope. Because the slope is semi-log analysis, the Linus function must use the natural log of known values, i.e. equals Linus of the natural log of the y's and the known x's. In this table here, I've just done a very quick analysis just to chart up the line to show you that it works. So now let's work through the analysis where we get the solutions for our decline rate and our cumulative production. We'll start by looking at the data. We have our raw data, which records a date and a production rate. Then I just calculated the difference in days between these dates and made a cumulative days, and then I just plot up the raw data, which are the red points, which is the rate times the cumulative days. Then I apply Arps formula shown here in the Q forecast. And here's the formula as written in Excel. And if we click on it, you can see that it's using these values here for QI, DI, and B, and the days. And these values are just the highest observed production rate. This is the initial decline, which I just used a Linus function for a selected number of days. And I'll show you what I've done here. So basically I just used the first 247 days of the data. So this portion right in here roughly, I've used these data because I thought those would be fair. So I get a DI of 0.00593. So my initial guesses are the first observed or highest production rate, which we see here, and I've used the initial decline rate using the Linus function that I've shown here, and I've just guessed at the decline exponent at 0.5, a value between 0 and 1. And then I modeled the error, which is just the percent difference between the observed and the modeled rate. And when I sum that up, I get something around 258%. And over to the left, I've used the solver to solve this to get a 0. So let me demonstrate how the solver is used. First, I'm going to change these values over here in the solve column to my initial guesses. So this is going to be 2706039. This will be 0.0059, and that's already there. Okay, let me hit Shift F9 and watch the sum of errors. And you can see now it's saying it's about 219% with those values. So I want to get this to 0. So let's use the solver. I'll go to Data, Solver. And we're going to set the objective to the error, or this T11. We're going to want a value of 0. And by changing the DI, the QI, and the B values, which are T8 through T10. Also, I'm going to go over here to Options, and I'm going to check the constraint. And I really just want an answer that's not nearly that precise. And this will change how fast the solver works. So I'm just going to make this, I'll accept the 0.1 error. Okay. And we'll click Solve. and then we're going to have to wait a little bit. This can sometimes take minutes to solve depending on the precision and or how large the data set is. Okay, it's been a couple of minutes and the solver has finished. I'll say okay. And here I've gotten a solution of 0.9. I can live with that. And you can see that the values have changed a bit. And let's take a look at the graph to see how the solver solution looks. Looks pretty good to me. You can run the solver several times and you'll get different answers. So they really don't make that much of a difference. So now that we've gotten the Q forecast done, let's work on the cumulative production. And it's over here in column S. And I'm just implementing this equation. Here I've shown you how you program that in Excel. So it's a kind of a long-winded formula, and you have to be careful you get the right number of parentheses on this formula and in the right place, or you won't get the right answer. But as we look at it, we can see we get a nice smooth trend, and we take it out to 1,500 days. And what I've done at the bottom of this data set, I've added some days in here and then calculated the production because I wanted to know what the production would be after 1,500 days. And we can see here that it's somewhere around 719 million standard cubic feet. And now just a couple of additional comments. So we've gotten what we wanted. We found out what the cumulative production was for our well, or the EUR. But there are different ways to solve for the cumulative production. And one nice thing about the formula is that you don't really need to set up any more tables to do it. You could do it in your original raw data file. But what I've done here is I've just incremented days down to 1,500 and calculated it with the increments of a day and got the cumulative sum. And I've charted it here, and this is going to be method 1, which is the orange line. The black line is what we got from in our raw data set. And another way to do this would be if you just took your original cumulative days, but they're not evenly spaced, and you get your decline and then you cum it up, and you can see that you get a blue line which underestimates. The fewer days or the fewer increments, the more you're going to underestimate the cumulative production. And here I've shown what you get from the Arps formula, from method 1, which is the orange line, and from method 2, which is just the observed data. And if we look at that, the difference between methods 1 and 2 is about 5%, and the difference between the Arps equation and method 1, where we incremented by 1 day, is 0.2%. For more information on how to do these analysis, I recommend these links which I use to set up this Excel dataset. Thank you for listening. Like and subscribe.